Welcome to today's lecture. This is lecture number 2 in Unit 2. And in the last lecture, we have started discussion on transceiver architectures, where we listed various architectures on receivers and transmitters, and we started with the general consideration of a limited bandwidth. Now we saw the constraints which a wireless communication environment is actually imposing on the design of both transmitters and receiver. We specifically we looked at the difference between band and channel, and how this band selection and channel selection is done by the process of heterodyning in order to relax the requirements of the Q factor of the filter at the front end, and also to reject the in-band and out-of-band interferers in stages. Then we looked at the basic operation called as heterodyning or mixing in a receiver. The ideal mixer will have two frequency components, sum and difference component. And for receivers, we generally focus on to the down conversion process, which is called where you will utilize the difference component. Followed by that, we also saw the general architecture of heterodyne mixer, sorry, heterodyne receiver, where we saw that two filters will be used in the structure, one at the front end as a band select filter in order to select the band, and later we employed a channel select filter in order to select the channel at the output of the mixer, where you have both the sum and difference frequencies. Then we also mentioned about two types of down conversion mixing, where you have by keeping a constant LO frequency and by generating various intermediate frequencies, and the second method of keeping a constant IF by varying the LO frequencies. That is generally done with the help of a synthesizer, which also will be discussed later in this course in last unit. Uh, then with that, yeah. So in today's lecture, we will continue the discussion on the same heterodyne receiver. Probably you are aware about the fact, or you would have heard about this called as the problem of image in heterodyne receiver. So can I get some response from you guys? Are you aware, or whether you heard about the problem of image or image frequency in heterodyne receivers anywhere? Mm, can I get some response? Oh, all right. This is the first time you are hearing to this. All right. Yeah. So let's see what is this, the problem of image, and we'll also see what can be a probable solution. And by introducing, or by after mentioning the solution for the problem of image, we will also see. So our discussion is mainly focusing, or is with this present architecture, the very primitive form where you have two filters, one for selecting the band and the later one for selecting the channel. So keep in mind that you have the same similar structure with you, where you have a band pass filter and a low pass filter. All right. Uh, yeah. So we start with this, the problem of image in heterodyne receivers. Yeah. So why, if you are wondering why we are still discussing the problem of image in a heterodyne receiver, I guess it is having importance in two folds. One is we will understand the problem of image and see the later developments happen in the architecture of the receiver. So what all other methods have devised in order to avoid this problem of image, right? So when you talk about image frequency or the problem of image, this is something which is very common in the case of heterodyne receiver. So uh, this is a very common problem in heterodyne receivers, because in heterodyne receivers we know that the problem of mixing is happening. So the process of mixing is happening. So to understand this, let me Let me bring in the frequencies here. One is the intermediate frequency, and one is the this is mixing. We have input frequency here. We have the local oscillator frequency, and we also have the intermediate frequency in picture. Right. So if I represent this in the form of a signal, I can write it as a cos omega ift, which is the intermediate frequency, is equal to a cos omega in minus omega LO into t. Right. Or this is same as writing a cos omega LO minus omega in into t. Right. Both are same. So what is the meaning of this? This means whether the difference frequency, whether this omega in minus omega LO, whether this is equal to a positive value. When I say a positive value, when you have omega in greater than omega LO, or a negative value when you have omega in lesser than omega LO, the difference, both are yielding to the same intermediate frequency, right? The only difference is whether your omega in is actually lying below, which is less than your omega in is less than omega LO or more than omega LO, right? That is the only difference. So to understand this better, let me draw this. So this is my input frequency, which is centered at a center frequency of omega in, and I'm using a mixer which is having uh, which which is having a local oscillator frequency omega LO. So whenever we go for this kind of mixing, that is whenever you have an omega LO greater than omega in, we usually call this as um, high side injection. So let me note down that here. When the LO frequency is above omega in, when I say above, it is more than omega in, we call this as high side injection, because the being the fact that the local oscillator frequency is injected, or local oscillator frequency is available at on the high side, or on higher side of the omega in. Now at the same time, you can mix with the local oscillator frequency which is smaller than omega in. If that is the case, when LO frequency is uh, less than omega in, we call this as low side injection. Right. So again, you will be thinking why we are talking about this. We'll come back to this shortly, where we have this LO frequency higher and where we have this LO frequency lower. So whatever it may be, consider this as the signal of interest. This is the signal of interest, or the input signal what we are focusing, which I expressed as a cos omega in t, and this is the LO frequency. So LO frequency is generally a pure tone, right? So this is the a cos omega LOT, and this is a modulated signal. Still I am expressing it as a cos omega in t, but assume that it is a modulated signal, right? Now, so this is actually these two signals are actually going to a receiver, or these two signals are actually going to a mixer. This is going here, and this signal is coming to this point, and at the output I will have omega in plus or minus omega LO, which is further low pass filtered by, and you will get omega in this case, since your omega LO is larger, I can write the difference frequency omega LO minus omega in is what I am expecting, right? So look at this, your input frequency is, so what is this difference here? The difference between your LO frequency and omega in is what is your intermediate frequency, right? So this is your intermediate frequency. Now, if at all if at all if there is an interferer or some other signal, if it is present at the same frequency away on the other side, which is somewhere here, if such a signal is available here, what will happen? This entire we know that we have received a band in prior and we are operating on that band. Now your desired signal omega is at this point at omega in, and you are injecting a local oscillator through the mixer, and now the mixing operation is going to happen. So we have introduced a local oscillator frequency at a frequency, particular frequency away from omega, and that is nothing but your omega IF for the intermediate frequency. So when mixing happens, the difference between omega L and omega N is your omega IF that you are getting. Now, if at all there is a signal, if at all there is a interferer present at equal distance on the other side, on the right side of the omega LO, that signal also, this signal also will be down converted, or this signal also will go to the mixer, that will also get down converted, and that will also fall to the same intermediate frequency, right? So if I look at that, let me draw that, then you will get a better picture. So now I have an intermediate frequency here, omega IF. Now we know that we want this input signal to fall at this omega IF. That will definitely fall through the mixing operation. And now if there is a signal which is available at the same distance, so that same distance is nothing but 2 omega IF away from the input signal, right? So for that particular signal also, after mixing operation, it will definitely fall on the same intermediate frequency. Now, if this is happening, both the spectra are actually getting overlapped, or the intermediate, the one frequency is falling on the exactly on the input frequency, and that is corrupting the signal spectrum. Right. So this frequency, which is at 2 omega IF distance away from your omega in, is called as image, which corrupts your signal later. All right. So this is generally called as a problem of image. I hope you guys understood what I am trying to convey from here. So if I am locating the image frequency, I can say that image frequency is located at 2 omega IF away from the input frequency, or this can be also this can be further, you can modify and you can understand this in a better way, right? So your image frequency is basically 2 omega IF frequency away from your input signal. All right, so this always corrupt your signal, and this will create, definitely this will create problem. You can think of how this will affect, because this is directly falling on the spectrum and corrupting your signal at that point. So are you guys with me? Do you agree that this is a problem, and images or certain signals can fall on the input? All right. Why just that 2 omega IF frequency? There are other multiples of frequencies as well. Yeah. No, it is not. I'm not telling that there are multiples of frequencies here. Now, why this itself, this is a specific problem, is because you look at this, you have input, you have a signal which is at omega in, right? And I have introduced omega LO at omega LO, and the difference between omega LO and omega in is omega IF is what we understood, right? Now, if the image what I am locating, or the image what I am telling, is also only omega, so if there is a signal present exactly at the same distance from omega LO, will only fall on that specific frequency. All right. So other frequency. So as we are down converting to omega IF, or as we are down converting to image frequency, apart from input signal, which other signal will fall on that input frequency? Only a signal which is available at 2 omega IF distance from the omega in. So that is why this is a problem. So I'm not telling that other signals or the other interferers are not a problem, but this is a major problem, because we are relying, or we are depending on the process of mixing and the output of mixer. Is that clear, Lalit? All right, yeah. So, what do you think? What can be a common solution to this problem? So you have something called as image, which is located 2 omega IF frequency away from your omega in, but that image signal is also down converted to the same intermediate frequency, thereby corrupting your desired signal. So what could be a probable solution? Yes, we know your question is image. You are referring to the interferer in the signal selected band, which is a yes, yes, Vinod. Yeah, you have a further question on that? Okay, yeah. Now, what do you guys think? What can be a probable solution for this? The easiest solution for all these things we will think is another filter only, right? Because if we can employ a filter which can reject images, then that would be helpful. Maybe duplicate the message signal that frequency. Which frequency? At 2 omega if, all right. But still that if an interferer is there, how will you solve that issue? All right, so let's discuss that. So the solution to this image problem, solution to the problem of this image, the first hand solution is, or a common approach what we generally take is to suppress the image. And whenever we talk about suppressing the image, we usually take the help of a filter. So to suppress the image, the common approach is, the most common approach is to use a filter. Where to use the filter? The filter should be employed just before the mixer. Filter before the mixer. And since the role or the main intention of introducing this filter is to reject images or to remove images, we call such filters as image reject filter. So even though I am proposing that the solution to this image problem is to use a filter, we understand that it is not that easy to have to introduce a filter. Definitely, we have to look at the other aspects. So, in order to discuss that, let me draw the. I'm just trying to develop the structure now. We have an LNA. Previously, LNA was followed by a mixer, but now I have to introduce one more filter here. I will call that filter as image reject filter. This is image reject filter. Now that filter will be given to the mixer, and where you are providing this omega LO, this is omega in, which is filtered out to produce your intermediate frequency, and later we have to process this. All right. Now, now here comes again the question. So, how efficiently how efficiently we can remove these images, or this is again boiling down to the same discussion, because we know that if you want to introduce a filter to sharply with a sharp cutoff filter, we should have a high selectivity. And if I go for such high selectivity filter, then if the so high selectivity means again that depends on the sender frequency, because everywhere we can relate that the Q factor or the selectivity is related to sender frequency divided by bandwidth. Now say if I am going to introduce a filter here as image reject filter, the sender frequency remains the same because we did not do down conversion. So we have to work with the same sender frequency of before. So the Q requirements is very high, or we have to actually develop a filter with high Q. Right. Now, all right, 1 second. All right. Now let us look at this structure, and let us look at the spectrum now. So we are introducing a filter, and the idea of the filter is you will have an image, you will have your input signal here. Now you have your image frequency located somewhere here. This is your image frequency, and this is located at a distance of 2 omega if. All right. Now, so if you look at this diagram, you can see that there is an image, input signal, and there is an image. Now, if I am introducing this image reject filter here, the idea of this image reject filter is to filter out the images. So what I'm expecting is the filter should actually uh, filter out the image and should take only this input signal, right? So, but we cannot say that the filter will be sharp enough to completely reject the image, or that depends on several factors, right? So, one question I want to ask here now: what do you think? What best way we can reject the images? So, what should be the condition on which we can reject the images in a best way? So, yeah, are you guys getting my question? You have now on the screen, you can see that there is a signal and there is an image, and you are introducing a filter here between LNA and mixer, and we call it as image reject filter. Now, if you want to reject, or if you want to remove images completely, what should be the condition? Because why I'm asking the condition here is, we know that the input signal and image frequency is located only at a distance of 2 omega if. Now when I talk about this image reject filter, the image reject filter is basically uh, that filter center frequency is not yet shifted. So what do you think, how you can reject the images well? Or let me write here the how to maximize image rejection. Omega im minus omega n must be large. Yes. How can we say that? So to maximize image rejection, see, it is very clear. You can see this is the characteristics, or the characteristics of the filter. Now, if this omega in and omega im are well separated, or if this distance, if 2 omega if is sufficiently large, it is easy for the image reject filter. So why I am telling it is easy for the image reject filter? Because when you are introducing a filter, the center frequency of the filter is still high, and the Q requirements are also very high. So practically realizing that is not possible. So in order to best reject images, if you have your omega if sufficiently large, then that will definitely help. How that will help? If your omega if is sufficiently high, if this is, sorry, there is an issue with the device what I'm using. Yeah, so if your omega if is sufficiently high, what we can do is we can definitely relax the requirements of the image reject filter. Relax the requirements of image reject filter. So why we need to relax the requirements of image reject filter? Because we are talking about designing a filter still at a higher frequency. So we have somehow we have to compromise on that, and compromising on that design and by rejecting the images properly, the only possible option is if your omega if is sufficiently high, 2 omega if will be still higher, and by relaxing the requirements of the filter with say some kind of this response, you can sufficiently you can reject the images, right? So will that lead to some other problem? Okay, I think I have some create some DC offsets. Who choose large omega LO. Choosing large omega LO, yeah, choosing large omega L is in turn increasing the distance between omega IN and omega IM, right? That is right. So did you guys understood this? You guys understood this problem? To maximize image rejection, you want to increase intermediate frequency. If that is clear, now tell me what is the problem if you maximize or if you increase omega IF? Will it affect the later? Will it affect later stage? So now I just made omega IF sufficiently high in order to relax the requirements of the image reject filter. But what comes next here? So after mixing, there comes your channel select filter. Now channel select filter center frequency is at omega IF. Now if your omega IF is sufficiently high, then you have problem again with the channel select filter, isn't it? Because you are actually making the Q requirements of the channel select filter high. So what you can see here is you can clearly see there is a trade-off between image rejection and channel selection. That is what the point we need to understand here. There is a trade-off between image rejection and channel selection. Let me keep a diagram here. I think that will give a little more clarity. All right. So what I was telling is, you have two filters. You have two filters. One is image reject filter and another is channel select filter. So where is the channel select filter coming in? The place of the channel select filter is somewhere here. This is the low pass filter which we called as channel select filter. This omega IF. All right. Now let us try to understand the trade-off here. So in order to reject images, reject image frequency, what we are doing is we are keeping omega IF large. Omega IF is kept large. Now by keeping omega IF large, what we are doing is this is leading to the Q factor requirements of channel select filter. Then Q of channel select filter will be high to practically make it possible. It will be high to practically achieve it. But why did we keep omega F large? To sufficiently reject images, right? So that is one thing. And the second thing is, if so, because of this problem, if I am keeping, if omega IF is kept low, then we can definitely make the channel select filter better. So then your channel select filter, I'm using this notation CSF, channel select filters Q can be made reasonable, but image problem will be still there. Will be there. and this can be well understood from this picture, the what you are seeing on the screen. See this is your desired signal, this is the desired channel here, and this is the image, right? Now I want to design an image reject filter, and since the image reject filter center frequency is high, I cannot make it practically possible, so I have to relax certain requirements. So in order to make the image reject filter design relaxation, to give that relaxation, I just kept 2 omega f sufficiently high. So it is high. So you can see that the image reject filter can sufficiently reject the images, right? But with the same condition, if I look at channel select filter, see, not only images, apart from images, along with the desired signal, desired near to desired channel itself, there will be other interference. Now I made omega f large and I rejected images, but when it comes to channel select filter, since omega f is large, channel select filter is not the q values are not practically achievable, and we are not able to generate a very sharp cut of channel select filter that will result in leaving apart some of the interference within that, right? But if you look at the image is very less there, but the interference are not completely removed because of the high requirements of the channel select filter. Now if I try to keep omega f small in order to reject the interference very close to the channel, what you can see, when you keep omega f very small here, see, we can have a good filter here, low pass filter, and you can reject even the interference very close to the channel. But see what happens here, since your omega f is very small, the image filter is not able to reject the images completely. So as a result, you can see image, uh, as a result, you can see there is a lot of corruption in the desired signal. So this is basically a problem, and we call this as, or this is basically a trade-off problem. If I try to keep a good image reject filter, then I have to keep omega f large, but that will result in interference within the very close to the channel, or the other way, right? So this is a trade-off between, there is a trade-off involved between image rejection and channel selection. All right. Now, so the takeaway from here is, since there is a trade-off involved between image rejection and channel selection, the solution what we proposed cannot be used, because there is always a trade-off. We have to compromise either on channel selection or on image rejection, right? So with that, in continuation to that, people have come up with some other idea, that is to solve the problem of image rejection and channel selection, that we will see now. So solution to resolve the problem, or the trade-off problem of image rejection and channel selection. Trade-off. There are multiple ways you can come out of this, and one possible way we'll discuss now. So before that, let me ask you this question. Are you guys with me? Did you understand what is what is image in a receiver, and like how generally we overcome the problem of image, and how that will affect the rest of the system? Whether this is clear? Can I get some response in the chat box? Yeah, so I'm directly relying on the responses what you're putting in the chat box, but I'm not very sure all 27 are listening to this what I'm telling. Right? If not, please do let me know if you're not able to understand, or if you're not able to focus. Right. So do you have any other solution in your mind, or do you have some other thoughts? How can we solve the problem of this image rejection and channel selection? We'll be discussing one standard solution. Apart from that, if something else is coming to your mind, let us discuss here. You can respond in the chat box. All right. So one standard solution in order to overcome this trade-off between this image rejection and channel selection is just to extend the process of heterodyning. So one One such solution is extension of heterodyning, the process of heterodyning. So what do you mean by extending the process of heterodyning? The meaning is instead of having one mixer, instead of having one down conversion, we can have multiple down conversion mixers. How it will help? Let us see how that will help uh, in the process or to resolve the problem between this image rejection and channel selection. All right. So so what we understood is everything depends on how we choose intermediate frequency, how far it is from the desired signal. Based on that, you can have a better channel select filter, or you'll have a better image reject filter. So the initial segments will remain same. We will start with this, the first band pass filter. I'll call this as band pass filter 1, followed by the LNA part, followed by LNA. Then so this is band pass filter 1. Let me name this as the initial filter, which is a band select filter. Now after LNA, we have this second filter that is also a band pass filter. I'll call this as BPF2, but the role of that filter is image rejection, right? So what we do is for this image rejection filter, we are actually trying to keep the intermediate frequency large only. So uh, after this, you will have the mixer, right? And I'll call this as mixer 1. Why I'm calling this as mixer 1 is we are trying for multiple mixers. Now one input to this mixer is LO frequency. Since I have multiple mixers, I call this as omega LO1. Now at the output of this mixer, what I'm expecting is omega IF. I am just putting this number 1 because this is the output of the mixer 1. Now after this mixer, what we have to keep is a channel select filter. So I'll use one more band pass filter there as channel select. So why I am calling it as band pass filter is because I did not I am not using a small omega IF and thereby getting a frequency which is on the low pass side. Still the signal is in the pass band. So I'm using another band pass filter for channel selection. Now what is the specialty of this is look at the first filter, which is the image rejection filter. After understanding the trade-off between this, in order to relax the so to reject image properly, I am keeping omega if large. That is what I am still following here. So intermediate frequency is kept large. Omega if1 is still large. Now, after this channel selection, we know that the channel selection is not appropriate, proper, because still there will be some more interference very close to the channel. So what we do is, after this, we employ one more mixer here. There we will use another frequency omega LO2, which can generate omega IF2, which is sufficiently low. Right, so we are doing two steps of down conversion, and this is your mixer 2, which is generating omega IF2. And after that, so the specialty of this is now your omega IF2 compared to omega IF1, your omega IF2 is still smaller. So with that, I can try for a channel selection where I will use a filter there, which is a channel selection filter again. So depending on the intermediate frequency what we use, we can employ either a band pass filter or a low pass filter. But now here we are looking only for two stages of down conversion, and this will be followed by the intermediate frequency amplifier and the other rest of the stages. Right. So the specialty of this is we have uh, of this structure uh, we are down converting the signal twice, and for that reason we call this receiver as dual down conversion receiver, or we call this as dual IF heterodyne receiver. For the reason from the names are coming from the structure itself, dual IF heterodyne receiver. All right. So let us understand the structure carefully. Initially, we have a bandpass filter, then LNA. Then you have the first image rejection, which is image rejection is done, and after that there is a mixer. But we will choose the local oscillator frequency of the mixer in such a way that omega IF is large enough. All right. Now then we will have the first band pass filter, which is again which is a channel select filter. But we know that still there will be interference because channel select filter is because of the omega IF value which we have chosen as large, channel selection will not be complete. So for that, in order to avoid or to balance the trade-off what we have seen just before, we will do one more down conversion and make IF2 very small, and then we'll do the final channel selection and get the desired signal. All right. So this is what this is what the structure of a dual IF receiver or dual down conversion receiver, and let us look at the output spectrum of this. I hope you can see this. So let me mark the various points here. Yeah, this is the initial input. Let me mark this as A. Yeah, so look at this. This is the first image here what you are seeing. So this is a desired signal at a particular frequency, and these are in band the interferers close by, and this is the image signal. So what we can understand is this is at 2 omega IF, right? This is the input signal. Now after band pass filter, at the output of the band pass filter, I just mark it as B. That is what you are seeing here. So it is filtered. So we are still receiving a band. Yeah. So these are the out of band interferers and these are in band interferers. So we received a band something like this. So that is what you are seeing on the second image B. Now after that, after B, you have a filter here. Yeah, so this is LNA, not showing the amplifications here. Yes, Neha, that is right. This is increasing the complexity. Yes, because we are doing one more down conversion. That is not so easy to incorporate everything together. But this was a standard solution which is available even that time as dual down conversion. But we will slowly discuss the other solutions, because even without having a much complicated structure, we were able to come out of the problem of image rejection, and that is done with the help of something called as image reject receivers that we will see shortly. Since this is one of the standard architectures available, we are just learning that. All right, so I'm not telling that this is the ultimate thing, but this do serve the purpose. All right, so I'm not showing the LNA output here. Now the B point is bandpass filter, so the image rejection, and the output of image rejection, let us see. What we are expecting is this is the image, and because of the selection of the intermediate frequency, we are able to reject the image almost fully. You can see the images are gone in this form. Right, now that is C, and after C you will have D, the mixer output. So you can see that this small portion is available here. After mixing, very small portion is only corrupted in the desired signal. Right, so that is the point D. Now after D, you have a channel select filter. So I'll just mark this point as E. So what you can see is, yeah. So after channel selection, you can see that that is point number E, right? Yeah. So E. So here you can see the in-band interferers are large. So after filtering, it is actually it has come down to a lower frequency, and still there are interferers, because since we have kept omega IF large, channel select filter is not a perfect ideal filter. So the interference close by cannot be rejected completely, and this shows that the frequency is actually reduced because D is at the output of the mixer. So this symbol shows that the frequency has come down to the lower side. Right. So this is happening here now E, and after E, you have another mixer to get the second intermediate frequency. So from E to F, still your frequency has come down with the in-band interference with this in-band interference here. This is just a mixing operation happened there. Now after that, you have the next channel select filter, but now since your omega IF2 is small, you are having a better channel select filter, and you are able to come out of the close by interferers also, right? And finally this is getting amplified, and this is the result of the amplified result, where you have the desired signal and there are small corruption coming from the images in the stages. All right, so this is a spectrum of the dual IF receiver, where we are setting two intermediate frequency by two down conversions subsequently, thereby resolving the trade-off which was happened before between the image rejection and channel selection. All right. So yeah, so with this I am winding up for today. We started with uh, the problem of image, and we saw the solution, the first solution, then we understood the trade-off, and then later we suggested uh, even the solution for the trade-off with the dual down conversion receiver. All right, so if you have questions, you can ask, and if not, we'll wind up our session. Thank you so much for joining.